Good morning. Glad to be here. And I thank the organizers to call me, invite me to give these lectures. Generally, when you talk to and said that you give history, you are becoming history. So, I was a little scared also. But nonetheless, let this be an interactive session, right? Let's explore things together. You're all PhD scholars, so you're here to explore things. You're here to you're in your field to explore things. So we'll do that exploration rather than I just lecturing and you going home. And since anyway it's a history thing, so let's start by why DFT, right? So let's start with that. And since this is an interactive thing, so I'll start with the simplest problem: particle in a box, right? So let this go to infinity. And I put one electron here. Everybody knows the solution? X equals 0, X equals L. What is the solution? Say that again? Okay, so that's very nice. It's root 2 over L sine n pi over Lx. Very good, right? And how does the wave function look? Ground state wave function looks like this, right? Okay. Now let's complicate the issue a bit. Put 2 electrons here. So x1, x2, x equals 0, x equals L, and they are interacting. Let's say some number, let's put it q over a square root of x1 minus x2 square plus some a square. A is very small than 1. Give me the wave function now. What will be the wave function? So what is the wave function? Psi x1, x2. Any ideas? Yeah, you solve that ODE right there. You solve the ODE and tell me the answer. Can you solve it? Do it, please. I'll be very happy. What are the boundary conditions? Boundary conditions? Any ideas? So I thought we were going to talk to each other. X equals? Okay. And any combination, right? Okay. So in any case, it vanishes whenever one particle hits here. Okay. Then how do I solve it? Could you speak louder, please? Is in infinity? Oh, I didn't write that? Yeah. Any attempts? Is the force repulsive or attractive between the particles? Repulsive. So they repel each other. So let's do one thing. I mean, is there anybody who can find the solution? So, I mean, the simple answer is you can't solve it analytically. So let's use a different chalk. That's fun. Yeah, cannot be solved analytically. All right. So we'll do it numerically. Have you people been doing any computations? Yes or no? Yes. So you'll make grid points. Suppose I make n grid points. Right? How many grid points would I need for two-dimensional problem? This two-particle problem. N square, right? N square. So n square grid points. For 2 electrons. Take 70 electrons. How many grid points? N raised to 70. Can you solve it numerically? Do you have that kind of memory? Yes or no? I have 70 raised to whatever, n raised to 100 grid points, 100 raised to 70. Right? So you can't really solve it numerically also. You have to develop approximations. Right? Necessarily. Right? So Schrodinger equation for interacting problems cannot be solved. Okay? Now let me ask you something else. Suppose I say that although I cannot solve it intuitively, I know things are zero out here. Intuitively, can you tell me what is the probability of finding one of these particles somewhere? How would the graph look? I cannot solve for the wave function, but intuitively, can you tell me how would the graph look? So I want to find the probability of finding one electron. And I'm plotting it with respect to x. How would it look? Like this? Yes? But they're repelling. They don't want to be close to each other. Would it get modified? Would it remain the same or would it be different? So you're saying like this, huh? So, okay. So there's a correction here. So let's make it with yellow. This is not correct. It will get modified something like this. Right? They'll repel each other. Does everyone agree with that? I could not even think of plotting a wave function, but I'm plotting the probability. Right? So why not use probability for doing your calculations? Yes? And what is this probability proportional to? Let's call it probability. Probability. I'm calculating at x. This is proportional to the density. Of electrons. So you see here, I did not know what to do, right? I had no idea. But here I can at least think what it looks like, right? What if I could use this probability in the calculation? Wouldn't that be really good? Right? It is also very physical. It gives you a sense of looking at things, right? If I can look at things, if I can imagine in my mind how things are looking, right? And I can at least plot it. And this is, so let's call it the density rho. Here it's a function of x, right? And compare with the wave function. The wave function was psi x1, x2, right? So this is function of x1 and x2. And this is a function of x only. right? And here the grid points kept increasing, n raised to number of electrons. Here grid points remain the same. Or let's call it number of grid points, right? And that's the motivation to work in terms of the density or probability rather than working in terms of the wave function. I'm still trying to calculate the many electron problem. I'm still trying to work in terms of electrons, but I'm changing the variable. And I hope I have motivated you that this is a variable which I can at least intuitively feel how it look, right? Wave function I can't even think about, right? Yes.
So, since we talked about 70 electrons and 8 raised to power 17, so how will I intuitively think of a density where there is 70 electrons?
Okay.
It's easier for 2 electrons to think of.
Okay, so very good question. So he's asking, how do I think of the density? So suppose I can't make three-dimensional, but nonetheless, look at this. Suppose there is a potential out here, right? Let's call it minus Z1 over R. Think of a molecule, right? Minus Z2 over R. And there you put a potential well out here. So this is a three-dimensional stuff, right? Intuitively, where do you think there are a lot of electrons going to be? Right? So here's a well out here. Let's make it like this. Here's a well out here. How do you think electrons are going to be distributed? Are they going to be more here or more near the well? Or let's make a valley also. Now that we are having fun, let's have more fun. So there's a hill, there are two wells and two atoms like this. Can you intuitively feel how the electrons distribute themselves? Right? There will be depletion out here, right? Yeah, so there will be more and more out here, more out here, more out here, right? And it still remains the function of the distance only. Chemistry, after all, is all about this intuition, how electrons are going to be distributed. So this is another thing. I'm glad you asked that question, because we always think you ask, you solve the equation and you get your answer. No. You think how things are going to work and then make the equations work accordingly. Not by cheating, but see if your answers are consistent. Does that answer your question? Or you're not satisfied, you can ask one more. Yeah, think about it. Yes.
Sir, for identical particles,
Yes.
Density is a very directly measurable quantity. You could measure where the electron is going to be.
Yes.
Does orbitals or the distribution of individual electrons, is that a measurable quantity? Or I'm saying, isn't density the fundamental quantity for a system of identical particles?
No, not necessarily. Depends on how you want to describe it. You're asking a question like, in thermodynamics, is internal energy the fundamental quantity or the individual kinetic energy of molecules the fundamental quantity? It depends on what you want to describe. Yeah. So it's a way of looking at it. Ab initio, yes, all the particles.
My question is, could we measure the distribution of?
No, you can't. No, so that's why you can even think about this, but you cannot think about the wave function so easily. So distribution is intuitively more, and you do measure that. Density is measured, yes. Just like in thermodynamics, you do measure the water density, but you don't see individual molecules. Right? Okay. Anything else? Okay. So is the transition clear that if I want to go, but this is intuitive. If I want to do it properly, I have to prove that I can work in terms of this quantity, which will be done in the next lecture. Right? But what we are going to say is that talk about initial attempts as to how to do it, and this will give you approximations which are used. Is the motivation clear? Any comments, questions? Okay. So I'll keep switching back and forth between density based and wave function, because ultimately we are doing quantum mechanics. It's just a different way of doing it. So the next question I'm going to ask is, where do you think I have the simplest possible density? So we are doing interacting electron problem. Right? And so I hope I have motivated that looking at density is easier, it's intuitively more appealing, right? And all the chemistry and physics and everything, solid state, comes through looking at the density. You look at valence electrons, you see where they're going. Now, if you're solving the interacting electron problem, so let's write the Hamiltonian, right? Which is, and I'm going to use atomic units. Or Hartree units, in which E equals h cross equals mass of the electron equals 4 pi epsilon 0 equals 1. Okay, so this is minus 1/2 summation I equals 1 through n Li square, that's the kinetic energy operator, plus V external R, which could be the nuclear potential and so on, plus Ri summed over I, plus summation Ij, I not equal to j, 1/2 1 over Ri minus Rj. Okay, so this is the Hamiltonian, which we cannot solve. We just saw in terms of 2 electron problem that I cannot solve for the wave function, right? So I have to make approximations. So initially, let's look at the wave functional approach, which is, now we have said that this is going to be approximate anyway. And I'm going to use density in an intuitive way. Okay, what we are going to say is that if these electrons are moving, and by the way, whatever I'm saying can be derived rigorously in a mathematical manner, right? So I'm just giving you the intuitive picture. So in this case, I'm going to say if the density of electrons, okay, so number one, let's assume electrons move in independent orbitals. All right. Why is that an approximation? So I'll keep, I had made, let me write that problem on the side. I keep going back to this, and you will see, you'll be able to answer all things. I have 2 electrons, and they have an interaction, which is like Coulomb-like, q over square root of x1 minus x2 square plus a square, right? Could I write the wave function as each electron moving in its own orbital? Was I able to do that? So when I write electrons move in independent orbitals, it's an approximation, right? And then potential and the density will come in is given by their density. All right. So the potential is going to be V external R plus integration rho r prime over r minus r prime d. When I write with the vector, this is a volume element, right? dr prime. But this includes all the electrons, so I have to subtract its own potential phi I, if this is ith orbital, r prime mod square over r minus r prime dr prime. This is going to be the potential that electrons move in. One is the external potential, the nuclear or whatever, right? And then from its own density, it creates an electrostatic field and it cannot interact with its own field. So there's this, I subtract its own field, right? And so these independent orbitals, let me write this as phi I, r, and rho r is going to be summation I mod phi I r square. Okay? And therefore, the equation for independent orbitals now becomes del square plus V external plus, let me call this V Hartree R. Right, this part I'm going to call V Hartree, since Hartree was the first who introduced this. Minus integral phi I r prime mod square over r minus r prime dr prime. This whole thing operates on phi I, gives epsilon I, phi I. So you see that problem that we were earlier addressing in the two particle problem in a box, we have reduced this to a simpler problem. Here is the assignment for you. Write the similar equation for this. Write the Hartree equation for this problem that we started with. Can you write the Hartree equation, assuming both are in the same orbital by Pauli exclusion principle? Phi 0, let's call it. Can you write the Hartree equation for this? So here's the assignment. Write the Hartree equation for the two electrons in a box problem. Okay? Can somebody tell me what it is? Assume the orbital to be phi. Can somebody quickly tell me what this equation would look like? Equation for phi I. Somebody has to give me this equation. In the meantime, I'll have some water. What is the equation for phi naught? Just make it from here. It's a workshop, so we can take it easy. It's not a seminar, so I can wait.
Minus half del square phi I.
My students are not supposed to be speaking. Equation for phi naught. See, if I tell you, do a DFT calculation, you go push a button on the computer and say, here's the answer. You have to tell me the equation. And then you'll say, I've done a DFT calculation, probably write it in the paper also. But this is classroom. तो ये हो रहा है ना?
They do not publish your paper in Pramana.
Until you write DFT.
Pushing a button, I can publish in Jets.
Yes.
See the difference.
Tell me the equation. I'm not moving until you tell me. If you want to relax, have a good evening, good morning, Kinetic energy operator. What is the kinetic energy operator in this? Minus. Okay, so let's do that. Minus half. This is one dimensional. Okay. Next. V is 0. V external is 0. What about the Hartree term? What is the density for two electrons if each orbital is phi naught? Rho x. Huh? This is phi 0. So what will it be? And this is one dimension, it's all real. Phi 0 square. Now tell me the equation. Plus? Self-interaction. So how would that come in? It's the only same orbital. So you subtract the same orbital. So it becomes this. Same orbital. So you subtract it. And that's very easy to see because one electron interacting with the other. That's it. So x prime, x minus x prime square plus a square dx prime obviously will go from 0 to L, right? Phi naught equals epsilon I, epsilon 0, phi 0. All right? Boundary conditions? It's not a wave function, it's an orbital, approximate orbital, right? At x equals 0, L is 0. Now, there is phi naught occurring on both sides. How do I solve it? Self-consistent. What does that mean? Okay. Very good. So they is solved to be solved self-consistently, right? Okay, let's write that. Suppose I still say that my wave function, right, is some sort of an, so assume a form, right, with some parameters that is solve it variationally, right? Then how would I achieve self-consistency? So I'll come to that now, because later when cone-sham is done, I want to do that problem analytically. So let's take helium problem. I'm just jumping over, right? In this case, you would have minus 1/2 del square, right, plus minus 2 over r. Let's write it z over r, helium like, right, in Hartree theory. Plus integration phi 0 r prime square over r minus r prime dr prime. All this acting on phi 0 give you epsilon 0 phi 0. Right? I've done exactly the same thing, except that now I'm in 3 dimensions. Right? Do you know the variational solution, very famous variational solution of helium problem? Simplest variational solution of helium problem. What does phi come out to be? Have you ever solved it in your quantum mechanics course? If not, then I have to tell you. Did you ever solve it in your quantum mechanics course? Helium problem done variationally. What is the answer? What does phi naught come out to be? Simplest is spherically symmetric. And how does it look? Any idea? Either you have to say yes or you have to say no. If you say yes, you have to solve it. If you say no, then I'll solve it. Huh? No, helium cannot be plane wave. Plane wave is for constant potential. This is hydrogen-like. So it has to be exponentially decaying.
But this is there in MSc curriculum.
Yeah, so they may have forgotten, but they have to say I have forgotten. Any idea? This comes out to be the square root of whatever a or pi cubed, e raised to minus z minus 5 over 16 r. If you don't know, I mean, part of these lectures is also what you don't know, so just go and learn it. What if I were to do this solution variationally? And I'll give you an idea of self-consistency. So I'll tell you what I'll assume, all right? And this is something you can do even for LDA. There are some problems you can solve analytically. So I'll assume that phi 0 is of the form e raised to minus AR, and obviously some normalization constant. All right? A comes with Bohr radius, so let's call it alpha r. If you calculate this with that, okay, then the potential phi 0 r square over all that comes out to be 1 over r, 1 minus e raised to minus alpha r minus r by 2 e raised to r by 2 alpha r. I think that's correct. It has to be alpha, that's dimensionless quantity here. All right? So what I'm going to solve is, so I'm assuming this form, all right? Minus half del square minus z over r plus 1 over r, 1 minus e raised to minus alpha r by 2 e raised to minus alpha r. All this phi 0 equals epsilon 0 phi 0. And you're supposed to want to do it in a self-consistent manner. And phi 0 I have already assumed is this. So to do it self-consistently, you take phi 0 to be some Cn with respect to beta e raised to minus beta r. All right? Calculate the expectation value. And I'm doing this because then you also can do exchange only cone sham in this manner for helium. So you don't really have to go to the computer. And then you calculate the expectation value with this phi beta minus 1/2 del square minus z over r plus this, let me call it, write it anyways, 1 minus e raised to minus alpha r minus alpha r by 2 e raised to minus alpha r phi beta. Okay, calculate this and do this. And this will give you beta in terms of alpha. Put alpha equals beta for self-consistency. And that gives you the answer, value of beta and alpha both. Okay, so that self-consistency comes because this orbital has to be a solution of this, but we're just finding a variational solution. Now I'm doing this because with this, you can also, if you keep changing the form of the potential, you can still solve it. All right? You can do it analytically, which is a nice thing about this. Okay, so DFT is not necessarily, or Hartree is not necessarily always numerical. In a variational form, you can solve it even analytically. Okay, so take that hand off like this from the computer, just like you take it off from your mobile. Don't get addicted to that computer tab. I use pen and paper. Okay? All right.
Principle of least action.
Huh?
That follows principle of least action.
Which one? Yeah, least action of the brain. Least action of the brain. You have to say brain also. Then something is least action, then what happens to that? Okay. So this is kind of introduction to what happens and what all you can do. And when I do my, I think I have an interaction session later tomorrow and a couple of days ago, we'll solve these problems. Because Professor Sen would have covered cone sham. He would have covered Hornberg cone. So we'll do these problems. This is a workshop. So put your mobile in room and put your computer in room and do it. Bring your pen and paper. All right? It's fun. I'm very happy, Somin, that you're doing this workshop because, everyone is going back to doing analytics. So, all right. Now, you see, when you do this, you still have this operator, which is a del square operator. And you still want to get rid of it because, part of the potential we got rid of through density, right? I'm not writing that horrendous looking summation ij 1 over ri minus rj 1/2 here. This has been replaced by this, which is simpler. I can at least think of in terms of writing some sort of an equation, single particle equation, right? I want to do more because I want to get rid of this. And that's where the earliest density-based theory comes. So before I begin on that, let me see if there are any questions or comments. So Shrey, comments you can do now. None? Any questions? Comments? So I have a trick in the class. Where's my mobile? So when students don't speak, I usually take their picture and show them how their faces look to me. At least smile, yeah, that's a good thing. And then they start talking because they don't like their faces being, looking like that. Any questions? Okay. So this problem that we solved here, right? Partly we have taken care of density, and that's simplified to some extent, right? The other extreme, so the other extreme is so this was a 2-electron problem. That's the simplest 2-electron problem, right? And the simplest many-body problem. The other extreme is infinite electron problem. And there are many subtleties, but right now we'll do the simplest one, and that is homogeneous electron gas. All right. So in this case, we have infinite number of particles moving in homogeneous, no potential, zero potential. So I have minus of del square phi I equals epsilon I phi I. Right now, no interaction taken. Okay. What is the solution? Plane wave. So you get phi I equals square root of 1 over L e raised to I k dot R, right? Where k equals 2 pi over L n, n equals 0, 1, 2, and minus also, plus minus, and so on. This is from the periodic boundary condition. Again, if you don't know this, go back and look up in your any quantum mechanics book, Schaff or Merzbacher or wherever. All right, this is plane wave. Okay, this is something which has become really the bedrock or backbone of a lot of DFT approximations. So that's why it's good to know about this. All right, so to start with, this is the normalization. Now, so this, let me write this. Periodic boundary conditions over L. That means phi x plus L equals phi I x and y and z. Okay. Now in this case, yes. Yes. So tell me, we are talking about infinite number of electrons. Mathematically, you're absolutely right. But wisdom-wise, 0. How would you put infinite electrons in L equals 0? Would you even dare do that? Right? So you have to ask questions. We're not dealing with physical systems, right? So this is thermodynamic limit. I have to take L large and large. You don't mind my pulling leg, right? I mean, do you? I have to pull your legs also. Okay. Now, so this is what it is. Now, in this case, for every delta K equals 2 pi by L, there is one state. Delta K x delta k y delta k z equals 2 pi by L, there is one state. All right? One space state. And each state there I can have 2 electrons by Pauli exclusion. Right? So for volume delta kx, delta ky, delta kz equals 8 pi cubed, let me just write 2 pi by L cube, there is one state. Okay? So I'm going to introduce now something called density of states in case space is going to be L cubed over 8 pi cubed equals V over 8 pi cubed per unit volume of K space. Any questions on this? I know this is a chemistry class, so this people who do solid state, and you must do a course in solid state even if you're doing chemistry, because I mean both are chemistry, physics is the same. One is infinite electrons, one is 2, 3, 70, 80 electrons, but basic methods are the same. So if I look at in 3D in this is Kx, Ky, Kz. For every 2 pi by L, there is one state, both sides. Right? And then obviously you can make this box also. There should be one out here. For every this volume, there is one state. And this volume is V over 8 pi cubed. The periodic boundary condition nahi laga. Ho jata gadbad. So there is one state in this, right? And L is, to answer your question, and you take tending to infinity and tending to infinity, such that n over L cubed is a constant, which is the density. That's why you don't take L equals 0. It's a thermodynamic system. If you take L equals 0, it will be infinite density. We don't have infinite density systems. Right? Okay. So that was in the lighter way I answered, but this is the real reason. Okay? All right. So when you take L tending to infinity, this is really very small. This is infinitesimal. When you fill all these systems, since the topmost energy has to be same, you fill a sphere up to some radius kf. All right? And if you fill it up to kf, what you get is the number of states in the sphere is going to be the volume of the sphere right, times the density of states. In each volume, there is V over 8 pi cubed, right? So that comes out to be, this is the number of states, the number of electrons is going to be 2 times, this 2 comes from the spin, 4 pi by 3 kf cubed times V over 8 pi cubed, and that's n. Are you with me? Is it okay? Can I proceed? Okay. So then, there are these two systems which are going to be very, very important for DFT. The homogeneous electron gas and 2-electron system, or absolutely lower limit hydrogen atom. All right. So this gives you, this cancels, right? It gives you pi square, and this gives you kf cubed over 3 pi square equals n over v, right? Which is the density rho. And this gives me kf equals 3 pi square rho raised to 1/3. All right, so you fill all the wave vectors, these k are known as wave vectors, up to highest kf. Then you exhaust all the states that give you up to n electrons. Is that okay? And this is the relationship. Now we'll calculate the kinetic energy. Now, beauty of this is because you can express everything. Remember, what is our aim? I want to develop things in terms of the density. So here I can calculate the density very easily. So let us calculate the kinetic energy of homogeneous electron gas. So let's see. I'll take the shell, this sphere, which is filled up to kf. I'm telling you all the tricks of doing it. So up to kf, what I'll do, I'll take a sphere inside of radius k and fill it up to delta k. All right. Then the volume of that is 4 pi k square is the area times delta k is going to be this volume. Is that okay? Yes or no? And then in that volume, I'm going to multiply by the density of states, V over 8 pi cubed, and multiply by 2 is going to be the number of electrons. Yes? And each electron in this has kinetic energy k square by 2. H cross is square, k square by 2m, but I'm taking Hartree units, so H cross is 1, m is 1, right? And then what do I do to calculate the total kinetic energy? What should I do? So I can write this dk. The moment you see d, you know the answer. What should I do now? Do that, please. It's okay. Can you do that? That'll give you the total kinetic energy of all these n electrons. So this again, 4 pi 2, this gives you pi square, right? Let's quickly do that. What is the answer? This is k raised to 4. So what are you going to get? K raised to 5. So you get 1 by 10 kf raised to 5 v. Over? I was faster than you are. Oh, pi also. Pi square. Yeah. Okay. I thought 5. Okay. All right. From this, I would like you to do it now. Calculate the energy per electron. From this, calculate kinetic energy per electron and express it in terms of the density rho. Yes. KF? This is KF, yes. Yeah, do it. Remember, so far I have not put in the interaction. But the beauty is that once you do this, interaction also takes care of itself. I mean, the solution final self-consistent comes out to be plane waves. That's why it becomes a kind of paradigm problem. What is the answer? You have the answer? Rho raised to 5 by 3. So let's write this. So there will be n times per electron will be n and the rest will be per electron. How much is that? That's okay. You can give me the total V times this. This is, we are going towards density based theory. So that's why I want you to do it. Maybe the habit of writing is gone, so fingers may be paining a bit.
Many are used to taking the photographs.
No, no pictures. They have to.
At the end of
I'm the one who takes the picture. Where's my mobile? I'll take the picture doing it. Yeah. And then we'll put it on the website of this workshop. And with a caption, people engaged in working out. So what is the answer? This is the total KE, yeah, because that's why V's term is coming. Total KE, yeah. Yeah, that will not. So let's write it total. That, I mean, from that you can calculate, divide by n, then you'll get that answer. Okay. So do it per electron. I don't care. 3 pi square. Two by three. Huh? Into 3 by 2. 3 by 20. Yeah. So let's see. This usually comes out to be 3/5 kf square by 2. So let me just check. 3 by 10, 3 pi square rho raised to 2/3. There's a factor more, half factor more coming here. It will be 310. 3/5 kf square by 2, yeah. Just check, maybe a factor of 2 mistake. In any case, this is the kinetic energy per electron, average kinetic energy. And therefore, this is rho is constant. Right? Any questions, comments on this? We'll do something more now. What we will do is now make an approximation. Anyway, we are doing approximation, so we cannot solve things exactly. So let's try that. Let us write, even if I have a atom, right, rho r, or a molecule, or whatever, let's write the kinetic energy, and I'll call this non-interacting because I've taken electrons to be non-interacting, right? Equal to, per electron is 3/10 3 pi square rho raised to 2/3. And if I take a small volume here, number of electrons out here is going to be rho r d r, with the dr with the vector is the volume. So I'm going to write this rho dr and integrate it. That's my approximate kinetic energy. And this is known as the Thomas Fermi approximation. So we have replaced that whole operator that was in terms of del I square, right, by this quantity. Now, obviously, once you make an approximation, you want to check it, right? So let's check that. And this will be for you to check. Take H like ions, so that phi r is equal to what? Z square over pi cubed or something, right? Some C here. C normalization e raised to minus ZR, right? The exact Ke is Z square by 2, right? Calculate using Thomas Fermi approximation. And compare. I'll leave that for you. Okay, but when we meet for discussion later, then we could do that. So you'll know what kind of, how good an approximation this is. So from that Hamiltonian that we wrote for the many electron system, now I can write approximate energy as Did you correct that factor of 2? So from this expectation value of the Hamiltonian, which was psi kinetic energy operator plus V external operator plus VEE operator psi, I can approximately write this as, right, integration 3/10 3 pi square raised to 2/3 integration rho raised to 2/3 times rho will come out to be rho raised to 5/3 rho r raised to 5/3 integrated over the volume. That's the first term, approximation, plus integration V external r times rho r dr. That's the second term, the expectation value of with respect to that, plus so we have replaced that entire energy by an approximate functionals written in terms of the density. This was the first approximation, first method developed to calculate, to solve for many electron problem in terms of the density, and this is known as Thomas Fermi approximation. Notice that in this case, all electrons are interacting with each other. So they are also self-interacting. Kinetic energy is approximate. This is exact. All right, so this came in 1930s. All right. Now, how do I solve this? So we'll write E Thomas Fermi rho as equal to 3/10 3 pi square raised to 2/3 integral rho r raised to 5/3 dr plus V external r rho r dr plus 1/2 rho r prime over r minus r prime dr prime. All right? You can check for, say, helium atom how good this approximation is by taking that e raised to minus z minus 15, z minus 5/6 r wave function. Any questions, comments? We have replaced that entire Hamiltonian expectation value. Rather than working in terms of the wave function, I'm now working purely in terms of the density. But we have to figure out how accurate these approximations are. But this was the seeds or beginning of density functional theory. Any questions or comments? Any questions? What about the equation for the density? Right now, we've just written the energy expression, right? And how would I get the expression, the equation for the density? Again, we do the variational principle. All right? So what we are going to do is take the equation So what we are going to do, I'll take rho r, vary it a bit, calculate the first order energy change and make it 0. Gives the equation. And of course, all this has to be done by keeping this total number of electrons the same. So which implies delta rho r dr should be 0. Okay? So let's do that. If I put rho r equals rho plus delta rho, what you will find is that delta E, Thomas Fermi, comes out to be, and you can do that, rho plus delta rho, take delta rho tending to 0, do the expansion, right? So you'll get 5/3, so that is 1/2 3 pi square rho raised to 2/3 plus V external plus integration rho r prime over r minus r prime dr prime delta rho r prime dr prime or the r. This is what delta E comes out to be. All right, you can just put that row, that I'll expect you to do. Keep terms up to first order. Here you get 2 terms. And this should be 0 when this is integrating to 0, right? So that means if I take 1/2, or rather I'll just write this is kf. Kf is square by 2, and this depends on R in an inhomogeneous system, plus V external plus V hot 3 is equal to some constant mu. This gives delta E to be 0. Because of this integral. Let me see if you follow that and if you have any questions or comments. Can you check that if I got it correct? Maybe I have a factor or 2 wrong. People here okay with it? You check that? Did anyone check from this side? What is that? There's no, this is H, not half. There's a factor of half? No. This will give you contribution from both sides, from here and here. So you get twice as much, so that 2 cancels. I'm happy you're working it out. So this is like the kinetic energy of the highest electron kf, remember, was the highest orbital, plus the potential, it should remain constant. This is a beautiful physical meaning. If this is not constant, suppose this is varying, from electrons from high energy can go to the lower energy and lower the energy. So highest occupied orbital has to have the same energy. Highest electrons have to have the same energy. Otherwise, they can transfer to a lower energy state and lower the energy. So minimization comes through that. Okay? And then this equation has to be solved. Again, self-consistently, because potential depends on rho. So when you solve this, this is like rho raised to 3 pi square two plus V external R plus integration rho R prime over R minus R prime dr prime equals mu. So either you can take a approximate rho, do it self consistently, or there are other ways of solving it. The standard ways by writing this as V total and writing del square V total equals 4 pi rho total, right? And with that, okay, which is 4 pi rho external plus rho electronic, and from here you get the del square V total you write from there. Okay, so you get an equation for differential equation for rho which you can solve. All right, so this has generated many papers because this is easy enough to model to solve, maybe not that accurate all the time. So there's a reviews of modern physics by Larry Spruck. I think it's 1993. Then reviews of modern physics by Elliot Lieb. I don't know the year, okay, but you can check that. And this, yeah, I'm coming to that. Then there's book by Norman March, who has done a lot of work on Thomas Fermi theory, all right, and many articles. If you write many articles by Norman March, he's done a lot of work. And this is, you see, if you look at it, this is an equation which has no derivative, right, of rho to start with. So wherever the potential matches mu, the density goes to 0. It does not extend all the way up to infinity for all systems. So it behaves like a classical system. It's known as semi-classical approximation, because in pure quantum mechanics, all the way functions go all the way up to infinity, right? And also you can show its equivalence to WKB approximation. All right. So, and this also, let me write this, forms the basis of orbital free DFT. This is the very first orbital free DFT. There are no orbitals involved, it's only the density, right? So one builds up, this is the 0th level, one builds up on this. Okay, and this was also provided the motivation whether one can write exact theories in terms of the density, which Professor Chattaraj will talk about later, right? Well, so how much time do I have? How much time do I have?
The old timetable says 11:15, but it says there is an update.
Okay, what is
Including my being presence itself is sort of big.
So-
So maybe another 5 minutes.
5 minutes? Okay. So I'll just, I think, stop here rather than going into artery fog and all that. This just gives the basic background of how density-based theory come. Then one can build up. So two really prototype systems you should think of. 1 2-electron systems, hydrogen helium atom, and homogeneous electron gas. Right now I derived the kinetic energy for homogeneous electron gas in terms of the density and use this as an approximation. You will see that the exchange and correlation and things like those, which will be talked about later, which are used extensively in DFT calculations, are also based, they start from homogeneous electron gas. I do not have time right now, but maybe in our discussion, the formal things will be done by Professor Kerisen and Professor Chatraj, but in our discussions we can discuss that more, how they come about. All right, I'll stop here.